differential equations yet. All right. As I was saying before I forgot to turn on Screencast-O-Matic, we're in Chapter 2, First Order Differential Equations, 2.3 Linear Equations, and we're doing the third example. This is on page 58 of your text. Okay, and here it is in front of you. Now, would you like to see me do this on the whiteboard rather than just reading the book? You can read the book. Would that be beneficial, or just go through it as is? That's what I thought too, but yeah, I didn't want to bore you with it because I know I'm so bad at it. So let's do the whiteboard. Okay, now here's another taskbar that, of course, is in the way. Let me get that is moved as far as possible. And also, well, now the whiteboard decides to write wherever it wants to. So let's clear that drawing. And let's see if I can move this just a little bit. I guess that's the best I can do. Okay, so here is our differential equation. X dy dx, and I didn't do that. Okay, the pen has decided to do a lot of its own writing today, so I hope this is not going to be a trend. Dy dx pretty ugly d's here. Okay, minus 4y is equal to x squared, x to the sixth, I believe that is. Yeah. E to the x. It's going to be an ugly, it came out okay. That's an X, not a T. Okay. I think I wrote the problem right. There is our problem. Okay. Now, first thing you need to make sure it is linear. Well, dy dx doesn't have any other y or derivative of y multiplied by it, so that's fine. First order, that's what we're dealing with in this chapter. Y doesn't have any other y or derivative of y associated with it, so that seems okay. And this over here can be any function of x. Well, I don't want to say any function of x. It really can, but we're hoping to deal with fairly easily managed. Even though it looks fairly complicated, we can deal with it. Now, this is a linear equation, but is it in standard form for a linear equation? Not quite. We want the leading coefficient. Oh, I should have said this. The only thing with the dy dx is a function of x. Only thing, coefficient of y is a function of x alone, which happens to be just a constant, minus 4. And this over here is just strictly a function of x. So it fits all the bills, but our standard form. Now, time out just a moment here. Remember, when we're doing some of the problems, we want it in what they call the normal form, which you isolate the derivative, the highest order derivative on one side, and have everything else on the other side. You don't want it that way in this one, okay? Remember, separation of variables, you want your dy's on one side and your dx's on the other side, all the y's on this side, all the x's on this side, and that's what you want. Not with linear. With linear, we want something that looks like this. The problem is we want this leading coefficient of your first derivative here. We want that to be a 1. It's not a 1, it's an x. So time out a moment here too. What we do to get rid of the x is divide by x. Well, when would dividing by x not be a good idea? x were equal to 0, because you can never divide by 0, right? But does that make any sense in this problem? If x were 0 here, this whole term would be 0, and you'd have minus 4y is equal to 0. That's not a very interesting equation. It's not even a differential equation. It's not a first order differential equation. It's not a linear differential. It's nothing of any interest. That would be only the value x equals 0, y is equal to 0. That's a point, a single point, and that's all it is. So we're pretty confident x is not 0, can't be 0. So what we're going to do is divide every term by x, because we want that leading coefficient to be a 1. Okay, so you divide that by x, divide this by x, and divide this by x. Okay, now here, the x's disappear, and you're left with dy dx I figured out, it never even dawned on me why I'm having so much trouble writing with this pad. Well, if you can picture the pad, I have to hold down the left key, the left button here, and I have to do that with my left hand, and then I'm writing on my little keypad here with my right index finger. Guess what? I'm left-handed, okay? But it's really awkward to try to hold down the left button with my right thing and then write with my left hand. Everything gets in the way. That's one reason my writing's so terrible. I'm left-handed. I'm not used to writing even with a pencil or pen with my right hand. No wonder it looks so bad. So here we have dy dx, and then your function of x, now I'm going to split them off. This is minus 4 over x, and that's going to be what your function, your coefficient function of x multiplying by y, and over here, this is equal to x will go into x to the 6th, x to the 5th time. Times e to the x. I was wondering, why am I so terrible at writing this? I'm left-handed, that's why. Okay. So now our function is in standard form for a linear function. Okay. Coefficient of your leading term is 1. This is a function of x alone, and this is a function of x alone. So we're okay. All right. Now, what do we focus on first? This thing that we called p of x. Okay. And if you recall, the p of x is assumed to be positive, so you incorporate the minus sign with it. So here, what we call p of x, that coefficient of the linear of the y, that's equal to minus 4 over x. My writing's terrible. Okay, minus 4 over x. What do we do with that p of x once we've identified it? Absolutely, take the integral of p of x dx, and that would be the integral of, I'm going to bring the minus 4 on the outside, if y'all are okay with that, and that just leaves me a 1 over x dx. Okay, now the next question is, what is the integral of 1 over x dx? Natural log of, oh goodness, that's ugly. Okay, okay, let's try that again. Okay, the natural log, my left finger didn't come up in time, of x. And we really probably should do absolute value of x, because x can't take the log of, now you can't take the log of 0, but we've already discounted the fact x cannot be 0. It's out of there. Nor can you take the log of a negative number. Well, nothing we've done here says that. So since we haven't excluded negative numbers, we have to put the absolute value bar there. We have excluded 0. That's out of the question. But we can't have a negative number there either, so we put that. So remember, on this integration, even though it's an indefinite integral, never put a plus c. You don't need one there. Now, what's the next thing we're going to do to this integral of p of x dx? It becomes the argument of your exponential function. You're going to e it, is what I say. That's a really lousy, stupid way of saying it, but that's the thing. Well, if I'm going to e this thing, I'd rather get it as a complete log function rather than a product of a log function times a coefficient. Now, what rule of logarithms allows you to do that? Do you remember what this is equivalent to? A times log x is the same as log of x to the minus fourth power. You remember that one? Okay. Now, let's think about what that's saying. That's 1 over x to the fourth, right? Well, guess what? It doesn't matter whether x is positive or negative. If you're raising it to the fourth power, that's always going to be positive. So therefore, I lost the absolute value signs here. And it wasn't just an accident. You don't need them anymore. All right. Now, what do we say we do with this thing? Yeah, raise it to the e. Now, do you see why I wanted it as a pure log? What does that give you? What is the e of log of x to the fourth? Natural log of x to the minus 4. The exponential function and the log functions are inverse functions of each other. So one undoes the other. You're only left with x to the minus 4. Do you remember that one? These are inverse functions of each other, so they undo, the e undoes the log, therefore you're left with just what's on the inside, e to the minus 4. All right, this now is what we call our integrating constant. What do we do with that? We multiply this integrating constant, they were calling it mu of x, by every term in the differential equation that we have in our general, whatever you call it, standard form. Okay, so let's do that. Even though it's tedious to write, we'll try to do it. That gives you x to the minus 4 dy dx okay, minus, now, x to the minus 4 is 1 over x to the fourth. And here you had a minus 4, ooh, that's an ugly 4, okay, over x, and when you're putting 4 more x's down there, that'd be x to the fifth, wouldn't it? Now, I may not like that form later, but we'll live with it now. Do you agree that's what multiplying this by x to the minus 4, it puts 4 more x's in the denominator. You already had 1, that gives you 5. And this then is, in fact, I'm going to backtrack. Sorry. I think I want it in the other way because I don't like variables in the denominators anyway. I did it to begin with because this is easier to see. It's antiderivative. But I'm going to now write this as x to the minus 5. Are you okay with that? So in other words, we now were considering this minus 4 times x to the minus 1. Multiply that by x to the minus 4. That gives you x to the minus 5. y, why not, is equal to, but over here, I'm going to pretend I did divide by x to the fourth, and that leaves me what? Or you can multiply x to the minus 4. X to the minus 4 times x to the fifth is x to the first, right? All right, so that's e to the x. This problem's looking maybe a lot easier now. Now, the whole purpose of doing this p of x, integral of p to the x, taking an exponential of integral of p to the x, all that was to get this integrating factor, and supposedly, if everything was set up, you had it in standard form, and you did all this, that guarantees that the left-hand side of this equation, this is why we put everything over here like that, is or should be a perfect derivative. And this should be a d by dx of your integrating factor, e to the minus 4, I mean x to the minus 4. Goodness gracious, where's my brain today? Where is it? Okay. Okay. X to the minus 4 times y. That's what we hope this left-hand side is a perfect derivative of that. Integrating factor times your function y. And this over here just continues to be whatever it is. Okay. Well, let's first, and I always do this just because I'm anal retentive. I don't know why, but I always like to take that derivative and make sure that what I'm saying this is indeed that. Okay. So let's take the derivative of that. D by dx of a product form is going to be the first times derivative of the second. E to the minus 4 times dy dx. That part is perfectly fine. Plus the second, y, that's good, times the derivative of the first. What's the derivative of the first? Minus 4 times x to the minus 5. Excellent. That is exactly what we've got there. So this is a perfect derivative. So this is supposed to be x e to the x, the left-hand side. Okay? Now, what I'm going to do, just because I hate writing on this pad, no, I'm just so bad at it, I'm going to write this in differential form, which basically takes the dx from here and moves it over here. It's kind of like I multiplied both sides by dx, but dx is not a number or anything representing a number. It's part of an operator, but I've written this in differential form. That's the correct math way to say it. Now what I'm going to do is integrate both sides. Now in this integration, since this is not a initial value problem, we are just going to integrate, and we will need a constant of integration. We'll worry about that later. Well, just like the exponential function and the log function were inverse functions of each other, so are integrals and derivatives inverse operations of each other. Okay? So when you take the integral of a perfect derivative, you just get what's inside. X to the minus 4th. Does that make sense? That's the fundamental theorem of calculus part 2, or some books call it the second fundamental theorem of calculus, or maybe that's the first one. I don't remember, but it's one of the fundamental theorems of calculus. Okay? That just gives you that. Now, how about this integral over here? Do any of you happen to know that right off the top? It's not something I store in my memory banks, because my old memory banks are wearing out, and I don't usually store stuff I don't need in them. So, anyone remember how you do that integral? if you don't remember what the integral is, which I wouldn't expect you to, how would you do that integration? There's a technique. Excellent, excellent. And which part would be part? What part is part? Okay. Integration by parts, you let one part of it, be a u, and we're going to let another part of it be a dv. This is ugly writing. Ooh. Okay, that's a v there. It doesn't look like. Let u be one part, and let the dv be the other part. Now, what part do you want to be the u? The x. Perfect. The general rule on that is pick the part that gets simpler when you take a derivative. That's exactly what we're going to do to this, is take a derivative. And the part that the d part, you're going to be integrating, you don't want it to get any more complicated. And that's what did the deal for me. I know that when I integrate e to the x dx, which is exactly, you put the dx over here with on the d part of it, okay? When you do that, it doesn't get any more complicated. If you did it the other way, you see, and let u be e to the x, du is also e to the x. Well, that didn't get any worse. It's about the same. But if you put the x dx over here, then that becomes x squared over 2. That's gotten more complicated. You don't want that, okay? So you've chosen well. The next step here is then du. Always, once you get u, you take a derivative of it. And du is what? 1 dx, right? Take derivative of this, you take derivative of that. Du is equal to dx. Over here, you integrate this, and this would be v. That looks a little more like a v. And what's the antiderivative of e to the x dx? E to the x. Now, don't worry here again about a plus c. If my memory's right, we don't fiddle with that yet. We let that work itself out. Okay? Now, is that right? I'm trying to recall. It's been a while since I've done integration by parts. Uh, yeah. Okay. So what you do with this side then is, what is the result of integration by parts? You do uv, which is merely x dx. I mean x e to the x. I can't even read. X e to the x minus your bottom line over here, the integral of v du, which is the integral of e to the x dx. Okay, and I think I could even do that integral. The first term is still x to the e to the x. Ooh, that's an ugly e. And that's not a very good looking x either. And what's the antiderivative of e to the x? I think we've already done it. That's just e to the x, my favorite function of all time. It makes derivatives and integrals so easy to do. So that's your right-hand side. And this is equal to your left-hand side, which is your x to the fourth. I'm running out of room here, but hopefully we're close enough to the x to the minus 4. Yes, yeah, we are. This is right where we do it too. X to the fourth times y is equal to x, sorry about that, e to the x, this is ugly, minus e to the x, and this is where you put in your constant. And I'm trying to think what's the best constant. I think just a plus c will do in this case. If not, we'll change it later, okay? Plus C, okay? Now, one more step you can do, since you got your y here, and that's the only place you got a y, and the x term here is multiplied by it, you can divide out, or in this case, multiply everything on both sides by x to the fourth. And that will get rid of this one. That will give you y is equal to x to the fourth times x will be x to the fifth. So ugly 5, yuck. E to the x minus x to the fourth e to the x plus c x to the fourth. There's your solution, your general solution for that linear differential equation that we started with. Let's see how the book did. Y is equal to x to the fifth e to the x minus 4 x to the fourth e to the x plus c x to the fourth. Perfect. Very good. Now, remember, and I forget this, I'd move on to the next. Anytime you solve a differential equation, you really need to focus on what is your interval of the solution, okay? Now, if you recall back from the very beginning up here, at this point, we said, well, at this point, we said x can't be 0. And here, we'd prefer for x not to be negative, okay? And if you want a continuous interval, then any x's greater than 0. So the interval of integration, you could call it, or interval of your solution would be all x's greater than 0. In other words, from 0 to positive infinity. Now, remember also, there really was no reason after we did this that you had to keep the x being negative, a positive. So it could be anything from negative infinity to 0. But you just cannot have x equals 0. That would find everything, okay? Of course, it looks like x equals 0 would be perfectly fine in your solution here, because then you have, and if x is 0, y would be 0. And that also fits the bill up here. Remember, we said if x was 0, then this term was 0, and you'd have minus 4y is equal to 0. X equals 0, y equals 0 is a legitimate solution for this equation. It sort of no longer becomes a differential equation, it's just an equation, but it is a solution. But when we divided by x, that meant we couldn't have x equals 0 anymore. So this is your solution when x is taken out of the possibility. And it could be either from negative infinity to 0, open parentheses, in other words, you don't count 0, or from 0 with open parentheses here to positive infinity, but it can't have 0 in it. Well, the point x equals 0, y is equals 0 is a singular solution, okay? A singular point in the equation, because it does fit up here and it fits down here, but it couldn't fit in our process here. So we only use this for x is greater than 0 or all x is less than 0. Either one would probably be okay. I think in this case, they did from 0 to infinity. I'm trying to think if there's any particular reason why they excluded the second part. Okay. I can't see it now. There may be a reason. but it just cannot equal 0 because that first step we took was divide by x, and that would not be allowed. All right, any questions on that? Well, let's go back to the, are there questions while I got this up here? None? Okay. Let's go back to the text and we'll see how they did it. And sure enough, that's the solution they got. And we're going to look at example 4 in a minute. So we'll deal with that then. I'm trying to see if there's any real reason they excluded the negatives here. There may be, I don't want to spend any time. So let's move on. Unless there's questions, let's go on to example 4. All right, so here's another one. We want a general solution for this differential equation. So let's go back to the whiteboard. X squared minus 9 dy dx plus x over plus x times y is equal to 0. Okay. Oh, here comes Dawson. Okay. Saw that one. Just happened to be looking at the screen when he came in rather than doing something else. So hopefully Dawson's here. He's connecting to audio now. So let's go back to the whiteboard. And, okay, Dawson, you there? Okay. We started and just finished doing example 3. Here it is, but I am recording. Hopefully it'll load. Now, let me tell you this, just in case it happens to you. My second class yesterday, which ran from 2:30 to 6:15, just before I went to bed, I went to check on it to see if if it had finished uploading to YouTube. And when I did, it had stopped midway. Okay. So I had to go back and redo it. And it was still doing then when I went to bed. This morning I came in and it had completed. Sometimes it does that. Now, I don't know why. It could be because it does take a long time to load, especially these long classes, uh, to YouTube. If the internet happens to hiccup, the spectrum, our provider has a moment or two of downtime or something, that could throw everything off and it doesn't upload properly. Usually it'll get it on the second try most of the time. Okay. And I have to fiddle with it and try to get it to work maybe multiple times. But anyway, if that ever happens here, you say, I thought he recorded this. It may be it had a hiccup like that and I'm having to go back and redo it. So don't panic if you don't see it, say, within an hour or two. It's never going to upload within it. Well, I won't say that. Number one, I'm going to be in class for the next 2 hours and 15 minutes. Then I'll have lunch. And then sometime after that, I'll get around to uploading. So it's going to be several hours, period. But if it's after that several hours and you still don't see it, it may be I was advising students most of the afternoon or something like that, and I didn't get a chance to do it, or that the system screwed up. Okay, and that happens. Know that it happened last night, so don't panic. So Dawson had time to write all this down, I'm sure, and he understands it completely. But if you want to hear it, just go back to YouTube video once it gets out there, and you'll be able to follow it. Do you need it any longer? Anybody? Okay. I'll clear the drawings, and let's do example 4. I'll look around for my ionizing pen. My fingers are my ionizing pen here. So here's the differential equation. Okay. X squared minus 9. I try to send it one way and it goes somewhere else. Well, now the eraser's not working. No, it's still not working. Okay, it does this sometimes too. Okay, do y'all have an idea? I wonder if clicking on this, I think this just makes it disappear. Go back to draw and then go back to eraser. I can't get it to happen. Let's try this. Let's close the whiteboard. Go back to here and then go back to the whiteboard. I'm fishing here, folks. Okay. No. How about clearing? That should work. Ah, that did. Now let's go back to draw again. Sorry. Let's see if I can get the pen to work properly this time. Open parentheses, x squared minus 9. And Dawson, I was telling the ladies here, I finally figured out why I'm having such difficulty writing on this keypad. I'm left-handed, but I'm having to use my left hand to hold the button down while I write with my right hand. I'm not used to writing with my right hand. I'm not ambidextrous, and I am terrible in doing this. So that's one reason. That's a 9. It doesn't look like it. dy dx. The whole world is set up for righties, not lefties. And that, by the way, is why left-hand pitchers sometimes have an advantage, because people aren't used to seeing them. And they say being left-handed in tennis is an advantage. I don't know if it is, not if I'm playing tennis, but or maybe I'd be even worse, which is hard to imagine, but that's beside the point. This is equal to 0. Now, the first question I always ask myself, is this a linear equation, a linear differential equation? Yes, the dy dx has no other y's multiplied by it, no other derivatives of y multiplied by it. The only thing multiplied by it is a function of x. That's allowed. The y has no other y's or derivatives of y's multiplied or divided by or anything else. So, and it says in the numerator it's a linear in y, and the only thing multiplied by it is a function of x. The thing over here is a very simple function of x, but it is only a function of x. There's no y's or derivatives of y's or anything else over there. So yes, this is linear. Is this in standard form? No. What we want in standard form is the coefficient of your derivative, and this is first order differential equation, so your first derivative to be 1. This has a coefficient function. So we're going to divide by that coefficient function. But right there, bells should go off, sirens should blast, flashing red lights should come on as you tell yourself, what can I not do? When is this not allowed? There are actually 2 situations now. Can anyone think of what those 2 situations would be? X cannot be what? Perfect. X cannot equal plus or minus 3. Let's see if I get my 9 to look more. Hey, that one that came out much better. And when I divide 0 by x squared minus 9, it's still 0. So I'm not even going to worry with writing that. So on this side, these go away. Understanding x cannot equal plus or minus 3. Okay? And on this side, this is what we got left. Okay? Now, I just as soon not write it again. So this is in standard form. dy dx is equal to x over x squared minus 9 times y equals 0. That is your standard form. What is the first thing you identify here? What they call the p of x. What is your p of x in this case then? Okay, my talking cut out or the whole thing cut out? Oh, I see. Okay, you're right. That's your P of X. Did it cut out for you too? Was it my bet? Okay, yeah. And again, I don't know why that happens. I didn't have the message come up, but I'm beginning to think this is a lousy microphone. This is a fairly new computer, about a year and a half. It came from the college. They invested in these really nice HP computers, laptops. But I have students complaining all the time, you turn your head, we can't hear you. Okay. So this microphone is right with the camera. And if I'm not talking right into it, the classes complain I cut out. But maybe I did move my head a little bit and that's why it cut out, or else it's a really lousy microphone. I don't know which it is, but whichever. What do we do with this P of X once we've identified it? Anybody? Integral of P of X dx. So that the integral of X over X squared minus 9 dx. Ooh, the nines are having trouble today, okay? Or my fingers having trouble. Sorry, excuse me. Uh, as I was telling Melissa this morning, had a great weekend, but I breathed an awful lot of dust, and not just dust, but straw and grass clippings and stuff like this. I mean, everything was a mess. It was a very windy, periodically windy weekend, and I was mowing and doing other things, and sometimes it blew right into me. And so, if I'm a little congested seeming, with good reason. Okay, so we got to integrate this. What technique would you think might work here? It almost looks like it's starting the same way as before, but this is a simpler form. This is how a lot of integration techniques start. Let, and the favorite variable is u. Okay, I don't think integration by parts is necessary here. Sim yeah, simple u substitution. Okay, let u equal. Now, what do you let u equal? Find the most complicated part of the integrand. Well, the x is very yeah, it's the x squared minus 9. That's in the denominator. I don't like my variables in the denominator. So that's why I want the innermost part of that part, let that be the substitution. Well, that's just going to be x squared minus 9. Let u equal x squared minus 9. You don't need a dv here. This isn't by parts. It's just u substitution. But the next line after a u is just by always, then u. Yeah, du is equal to what? To x dx. I think I heard in the background, du is equal to 2x dx. Now, there's different ways that different books and things proceed with this. I kind of like the technique that, I can't remember if this book uses it or not. I don't know. It doesn't do this. Here, up here in this integral, you have an x dx. You don't have a 2x dx. So what you do is divide out the 2's, okay? But if you divide this side by 2, you also have to divide this side by 2. So now over here you have a du over 2, but now you have x dx, which is exactly what you want. So this integral becomes, once you convert it to, not only does my head stopped up, my eyes get itchy like crazy. They're so dry now. So much mess came in on this weekend. All right, so this integral that you change from your x's to u's, the x dx is 1/2 of du, so I'm going to put the 1/2 out here, and I'm going to put the du where the x dx is. I'm going to put it in the numerator here, over, and your denominator here is u. Okay? Now, can anyone do that integration for me? I'll do the 1/2 part, save you that mental exercise. Log of u, natural log of u, and you really should say the absolute value of u too. So I'll try to write that in here if I can. And this one we never put a plus c. Okay, don't sweat with that yet. Okay, now, again, this is our integral of p of x. Okay, not quite. This is something of u. But what's one thing we're going to do to it? You're going to eat it, right? So again, we want to take the next step, and it doesn't matter whether you do it now or later. I just assume do it now and make this log of u to the 1/2. And here it's even more important to make sure that's a absolute value of u, because you can't take the square root of a negative number either. You can't take the log of a negative number, and you certainly can't take the square root of a negative number. You could take the square root of 0, but so u can't be 0. Okay, we've already said that, because if u were 0, that would be plus or minus 3. So x can't be plus or minus 3. We know that. All right, and at this point, I guess I'll put it off as long as I can. Let's go back to our x function, and that would be the log of, and now we'll put the u is x squared minus 9, so we put that in per absolute value bars, x squared minus 9 and then you're going to take this to the 1/2 power, or the square root of x squared minus 9 if you prefer to write it that way. Okay? Now, what do we do with this expression of the integral of p of x dx? As I said before, you e it, okay? And the e undoes the logarithm. So what we have here is your integrating factor is, if you want to call it mu of x, you can, x squared, the square root of x squared plus 9. So I'm just going to write it as x squared, I'll say plus, it's minus 9. Okay, let's do a timeout. I'm tired of writing absolute value bars. What would make this, what would guarantee that this stays positive? What values of x guarantee this stays positive? Well, it would be negative anytime x is between minus 3 and 3, right? Because x squared would then be something less than 9, correct? And that minus 9 would then be a negative number. So that means your x either has to be less than negative 3 or greater than positive 3. Okay? Now, I guess either one of those is fine. So those are two intervals we're going to deal with. And I was hoping it was going to be the other way around, but I don't think it is. So I think from now on, let's just say x is going to be greater than 3. Okay? You could say equal to 3, but you couldn't do it equal to 3, remember, for this reason. Okay? You can't divide by 0. So let's just say x is greater than 3, and I'm going to lose the absolute value bars. So this will be x squared minus 9. Where's my cursor? Okay, this is aggravating. There it is. Okay. Okay, so this thing here to the 1/2 power. That's your integrating factor. I would put square root, but you're not going to want to mess with the square roots anyway. So what do we do with that integrating factor? We come up here to our differential equation in standard form and multiply everything by that, okay? So it seems like we just undid that, but now we're going to go back and redo it. So let's do what we said here. This will be x squared minus 9 to the 1/2 power times your y. That's equal to, I'm sorry, I forgot where I was. Let's see as my eraser comes back. No, it doesn't. Yuck! Okay. I'll write it in here. dy dx, that's the left-hand side. I was already undoing that in my head. And that's equal to x times x squared minus 9 to the times y. Oh, this is to the 1/2. You're going to let me get away with that, weren't you? It's supposed to be to the 1/2 power. And this is equal to that integrating factor times 0 is still 0. Now that looks a lot worse than what it was to begin with, but the good news here, at least we hope it's the good news here, is that this thing here is supposed to be the derivative of, if I could get my pen to thing to move, d by dx of x squared minus 9 times y. That's where I thought it was before. Okay. Okay. So, this is terrible. Awful. Partly is my finger is sticking on the keypad for some reason. Sometimes it sticks and sometimes it goes crazy. Well, sorry, I don't need that. Okay. It's equal. This is supposed to be a plus sign here. Okay, sorry, I don't know how that became. And that's so this is supposed to be a plus sign here too. So that's pretty ugly. Sorry, I can't get my eraser to work anymore. It won't come up. Okay, and that's equal to 0. That's what I was writing right over here, but wrong here. So, let's see if indeed that is a perfect derivative. No, I'm sorry. The left-hand side is supposed to be this, okay? And the right-hand side is just supposed to be 0. Sorry about this. I've got it all crossed up. This is supposed to be a perfect derivative. Let's see if it is. Well, the derivative of this would be the first times the derivative of the second. And this is to the 1/2. Y'all are letting me forget my 1/2s here, okay? Okay, it's this times the derivative of that, plus y, there it is, times the derivative of this. Well, what is the derivative of this part? 1/2 of x squared minus 9 to the, and then that should be to the minus 1/2. I kept thinking in the back of my mind, this isn't working well, times a 2x. Well, that wipes out the 1/2. But this should be to the minus 1/2 then. And how did that not come out that way? Okay. Did I write the problem down right? Yeah, it seems like that's correct. Okay. Well, this is supposed to be this thing here. Oh, of course. This is to the minus 1/2. Okay. Sorry. I got all screwed up here. When we're writing this down, the integrating factor here is this. The left-hand side is just this thing times y, dy dx. Over here, you had this in the denominator, x squared minus 9. When you multiply that by x squared minus 9 to the 1/2, that leaves this is a minus 1/2 here, which is exactly what it needs to be. Part of the problem is my eraser's not working, so I can't see this stuff. And sure enough, when you take the derivative of this, now that works. Derivative of this is this times derivative of that, got it, plus y times derivative of this, which is 1/2 times x squared minus 9 to the minus 1/2, perfect, times 2x, that wipes out. Yeah, that is a perfect derivative of that. So what we have is that this thing is equal to 0. And then you do your dx on this side over here. In other words, write it on in differential form, and you integrate both sides. Sorry, okay. And this is just, seems like we lost Dawson. Okay, you're integrating 0 dx over here, which is pretty easy to do. We'll get to that in a second. So this would give you integral of a perfect derivative would be x squared minus 9 times y. Okay, Corbin is coming in. Good to have Corbin here today. Okay. Now, Dawson's coming back. I don't know. Should we let him back? Yeah, I guess so. So what we have here, and Corbin, you just come in. Sorry, the screen is a mess because my eraser has decided not to work anymore. Yeah. So there's just all sorts of mess here that I didn't want there. I wanted to erase. I couldn't. And now it's crossed me up when I'm doing. What we have here, we're doing, this is example 4 on page 58, chapter 2, first order differential equations, section 2.3, linear equations, and example 4 on the bottom half of 58. It carries over to the top of 59, but we're still here. Okay, we're integrating a perfect derivative, so that's just x squared minus 9. And the pen is doing whatever it wants to, but I can't erase that. Times y is equal to, now, what's the integral of 0? Antiderivative of 0. Just a constant c, perfect. Okay, so when you take a derivative of c of constant, you get 0. All right, so what does that yield us? That y is equal to c over x squared minus 9. Oh, it's x squared. Y'all keep forgetting. let him get away with this. That's to the 1/2 power. Okay? And you divide both sides by that, and that's x squared minus 9, the square root of x squared minus 9. But, or you could leave it upstairs and call it a minus 1/2. I don't care. Okay? But don't do both. Okay? Okay. So, c over the square root of x squared minus 9. All right. Now, again, we notice this splits our solution set into 3 regions. Okay? You could be over here less than, because x equal plus or minus 3 becomes vertical asymptotes here. Because again, you cannot divide by 0. So plus or minus 3 are out of the question, vertical asymptotes. Now to the left of the leftmost vertical asymptote, where x is less than -3, can't be equal to -3, so it has to be less than -3. This thing is positive because -4 squared is 16 minus 9. Yeah, that's going to be fine. And you can take the square root of positive numbers. In between -3 and 3 can't happen. Okay, even though that would be okay in the sense of not 0, it's not okay because you're taking a square root of that, and anything between -3 and 3, like -2 squared would be 4, minus 9 would be -5. Can't do it. Can't take the square root of a -5. So anything between -3 and 3, completely out of the question. Anything over here to the right of 3, yeah, that's going to be fine too. So we'll take the interval of this differential equation, where this would be valid, would either be from -infinity to -3, not counting -3, or from +3, but not counting +3 to +infinity. Okay, that would be your interval. Now, trying to see if there's any reason in the world why you would have to exclude the negative. The only thing that I can think of is because here you were taking logs, but we took care of that sort of with the absolute value sign. But if you didn't want to incorporate that into it, stay with +3s and you'll be in good shape. Now, and there's your solution that they got in the text. Any questions? Do you need this up here anymore, or can I go back to the book? Let's go back to the book. And you see here's their solution. Y is equal to c over the square root of x squared minus 9. And they say thus on either -infinity to -3 with an open parenthesis there, or from 3 to +infinity with an open parenthesis there, that's the general solution. On either part of that integral, you can do that. Okay. Now, the top of the next page is what they're talking about. Notice in example 4, the x equal 3 and -3 are singular points of the equation, and that every function in the general solution is discontinuous at those points. Okay. On the other hand, x equals 0 is a singular point of the differential equation in example 3, but the general solution allows that. There's nothing that says you can't do that. Okay. However, in the family of solution, okay, and they're going back through this again. This solution, just looking at the solution, you say no restrictions. Polynomials, exponentials, defined everywhere, no sweat. But you can't say that in the differential equation because the steps you took to get there excluded x equals 0. Okay? There's nothing wrong with x equals 0 here because that makes y equals 0. Perfectly fine. But you can't do it as part of your solution because first thing you did was divide by 0. Okay, you can't do that. However, the family of solutions defined that cannot be considered a general solution because that singular point still causes a problem. And so you have to do it either on the left or the right. That one, they just arbitrarily took the right-hand side, the positive side. I don't see any reason you couldn't do negative infinity to 0 left-hand side. They just chose the other. So again, not an issue. On the one we just did, it's obvious x cannot be plus or minus 3 ever. Okay, it doesn't work in your equation. It doesn't work in your solution, in your differential equation. So let's do another one like that, only we're going to have a initial value problem. That's going to be example 5. Any questions on 4 before we leave it? So here's 5. Let's see if we can get the screen. We can get the screen, but whether we can get it to work properly. I'm going to clear it. Anyone need this any longer? Okay. And we're going to start writing. Here's our equation, dy dx. Okay. Plus y equal x. Okay. This time we have an initial condition that y of 0, and this truly is an initial condition, y at 0 is equal to 4, I believe it is. Now let's see, 9:48, we go to 10:45. Would y'all have any objection to a bladder break? I don't absolutely have to have one, but I don't think I'll get through the rest of it. So do you mind doing a quick break? Okay, I'm going to turn off the, thanks for the break, but I can't make it another hour, so let's go with it. So here's our equation. That looks pretty simple, doesn't it? Pretty simple differential equation. You think maybe we could do separation of variables? Nope. If you move the y over to the other side, x minus y, those are subtracted. They are not multiplied. So nope, separation of variable out of the question. Now, the good news is they've already got it in standard form for you. The leading coefficient of your derivative is 1. So what does that make y to be? Well, what does that make? What do you get out of this term here? What do we look for? Your coefficient for the y is 1. What do we call the coefficient for the y term? Your p of x. And p of x here is simply the number 1. And what do we do with that p of x? We integrate it with dx. So the integral of p of x dx would just be the integral of dx, right? Because 1 dx is just dx. And what's the antiderivative of dx? Is anyone still there? Everybody took a break. Y'all back? Am I talking to myself? Okay, here. All right, good. Okay. So the antiderivative of dx is just simply x. Okay? So that is your integral of p of x dx. And what do we do with that? you e it. Okay, I've got you saying it now. Okay, you make that as an argument of your exponential function. So that's your integrating factor, e to the x. Okay, so what do we do with that? We multiply it by every term in this standard form. So that would be e to the x dy dx if I could write, plus e to the x times y is equal to x e to the x. I'm going to put the x in front of that one. I probably, okay. X e to the x. Okay. Not a very pretty x there. Yeah, that's a little better, maybe worse. I don't know. All right. Now, at this point, we say this left-hand side is supposed to be a perfect derivative, d by dx, of the product of that integrating factor, e to the x, times y. That's what it's supposed to be. If everything worked well, if we did all the steps right, that's what it should be. Now, what I like to do is check it and see if it is. Well, derivative, okay, derivative of a product is the first times derivative of the second, which is exactly what you got here, e to the x times dy dx. That part's right. Second part is plus the second, y, which is correct, times derivative of the first. Derivative of e to the x is e to the x. So yes, that is a perfect derivative. And that, they say, now is equal to x e to the x. Okay. And the next step, remember, I used to be able to erase it. I can't anymore. So we'll just wipe it out here. It's sort of like you multiply it by both sides. You really don't. You write it in differential form. That puts the dx over here. And now you integrate both sides of that. Okay. Now, the integral of a perfect derivative is just the argument. Why did it start with the x? I don't know. E to the x, y is equal to, now, for those who came in a little late, sorry, Corbin, we did a problem earlier today. We wound up with the same integral. It was a different problem. Does anyone remember what the integral of x e to the x is or was? If not, we'll redo it. Do you know? Don't remember? Would you remember the technique we used to get it? Anybody? We did it earlier. It's a product here. And usually when you have a product, those are going to be a little difficult to separate, unless this was, say, x squared here, and then, yeah, this would be a form of a derivative of that, okay? We don't have an x squared here. So now we do integration by parts. And the technique is this is the hard part, is writing the words, let x, or u, sorry, almost always a u, equal x. The part when you differentiate it, it gets easier to do. And dv is equal to the rest of it, and that's e to the x dx. You want that because when you integrate that, you don't want it to get any more complicated, and that's the beauty of the exponential function. It doesn't get any more complicated when you integrate it. Stays the same when you differentiate it, stays the same when you integrate it. So then this gives you your du, I should put a then there, but I just don't feel like writing. Du is then simply just dx. The d's always go together. Okay, if you have a du down here, you better have a dx with it. If you have a dv here, you better have a dx with it, and we do. And then the v, when you integrate this, is simply e to the x. Now down here, you don't worry about constant of integration yet either. We'll do that in just a minute, okay? Now, integration by parts follows that. When you do this, your answer is the product of these two, your u times v, and that is simply x e to the x, okay? There is your first part, x e to the x, minus the integral of the bottom line, e to the x dx. That's the ugly e. And we know what that is, don't we? Okay, so that would be your x, e to the x from the uv. It's supposed to be an x, okay? Minus an integral of e to the x dx is e to the x. Okay, plus the constant of integration. Don't ever forget that. Oh, yeah. Now, I think we're perfectly happy to go on and let this be c, okay? If we don't like it, we'll change it. But you see, this is a boundary value problem, so it should work out pretty well anyway. So what we have down here, the left-hand side was e to the xy. The right-hand side we've just worked out to be x e to the x minus e to the x plus c. All right, that's an ugly c, but we'll have to live with it. Okay, there is your solution. Now we haven't solved it for y yet. And now I'm beginning to think maybe we could call that constant e to the c. Let's leave it as c for now. And let's divide everything by e to the x, okay? And that will give us y is equal to x, because you divide e to the x by e to the x, I got minus 1. Ooh, that's way too long a minus sign. Minus 1 plus some c, some constant c, over e to the x. And that's why I wondered if maybe I should make it e to the c, and then that would be c e to the, or whatever. Okay. I think we're okay because we're going to use our initial condition. When x equals 0, y is equal to 4. So this would give us that 4 is equal to 0 for here, a minus 1 here, a plus c over 1, because e to the 0 is 1. So that would be c, if I could write. And then add 1 to both sides, and you get c is equal to 5. So your solution now is y is equal to x minus 1 plus 5 e to the minus x. Pretty ugly, but it's there. There's your solution. Because certainly when when x is equal to 0, that's equal to 4. And dy dx, if you take the derivative of that, you can go back and check it. Everything should work. Let's see how the book did it. Any questions on this before we go back to the book? Yay or nay? Okay. So let's go back to the book. Yeah. All right. So y is equal to x minus 1 plus 5e to the minus x. That's exactly the form they left it in. Now, in addition to doing that for us, they drew up a picture. Thank you very much, Billy, for giving me this so I don't have to try to describe the picture or hold the picture up in front of the camera. Here we have it. These are various C's that you could have here. And by the way, nothing we did in this problem had any asymptotic behavior. There was nothing that we did that said, no, X can't be this, Y can't be this. There's nothing, every value is okay. But when you have a form that looks like this, especially when you had the C in there, okay, here's what that looked like. In the first place, you see this term here for very large x's, this term is going to go to 0 because e to the minus incredibly large number is going to be 1 over e raised to an incredibly large number. That's a 2.7, or let's just round it to 3 over an incredibly large number. That's going to be, and c is any constant, after a while, guess what? That's going to 0. So then you have the function y is equal to x plus 1. That is a linear function, y-intercept of -1, and this one c is equal to 0. That's exactly what you get. You get that green straight line there, and that's where it's going to. And for very large x's, all of your solutions are approaching that thing. For small x's, this blows up. I mean, this gets incredibly big, and this gets negligible. So who cares about this thing down here? Your functions here do all sorts of things. When c's are negative, you're somewhere below this line. When c is equal to 0, you're right there. C is equal to positive, you're over here. And our c happened to be c equal 5 because when x equals 0, y was 4. They didn't put their scale, well, they did too. There it is over there. That doesn't look like it's quite in the right place, but pretty close to it. Okay, maybe it is. Okay. So there is the one and only one solution with the initial value on it. And what we call this, since ce to the minus x for very large x's, that sort of disappears. So we call that the transient term, because in the long run, everything winds up the rest of it. This is only what happens down in very small x's where that really matters, and then that wins the day. It takes over, and you just almost ignore the c equals 0 line. It's you don't really ignore it because it's pulling things down to it, but that's why this last term, 5e to the minus x, would be your transient term. For once you get past a certain level, that loses all meaning, and you're left with y is equal to x minus 1. Okay, now, next thing we're going to deal with is piecewise linear differential equations, which sounds like a real bear, okay? It may or may not be what we're going to do. In constructing mathematical models, okay, especially in the biological science and engineering, it can happen that one or more coefficients of a differential equation turns out being a piecewise defined function. So let's say that the p of x or the f of x, either one, becomes piecewise defined. And then you have what we call a piecewise linear differential equation, which is a mouthful. Okay. Next example, we're going to let the right-hand side, the f of x, be a piecewise function. The basic idea is to solve the initial value problem in two parts. One part for the first condition, one part for the second condition. See if error of the twain do meet. If at that point of transition, in this case, x equal 1, they line up. And if they do, you're in good shape. Okay? So, here is your differential equation. The first one you solve is dy dx plus y is equal to 1. Now, this is only good between 0 and 1. It does count 0 and it does count 1. It's the only place that's any good. Okay? And the second one is dy dx plus y is equal to 0. And that's anything beyond 1. Okay? So obviously this function is not defined for x less than 0. So these are only positive x's here. Now, you might ask why. Well, it's not clear why that would be the case, because there's nothing in the way the problem is lined up here that would indicate there's anything wrong with outside of that. It may be this is a physical problem that negative x's don't make any sense, okay? And if that's the case, fine, okay? So what we do is do your two different equations. And I guess we need to go to the whiteboard to do those because they're giving way too much away way too quickly. Okay, can I clear? I'll say yes. Okay, now, all right, just wondering if, now for some reason, Zoom is saying, please move this window away from the whatever. I can't read that application or whatever it is. That's the entire window. I don't know why they're saying this, but we're going to sort of ignore it. So here's a differential equation. Actually, it's two differential equations. I just as soon write it this way. Dy dx, I don't like writing it either way because this is, but y'all can see behind this window, right? When it's a small window at the bottom, it seems to block everything. But on this window, it's not blocking anything, is it? Dy dx plus y is equal to, and rather than writing the piecewise part, the f of x as f of x, and then saying what it is, let's just write the two equations. The first one is equal to 1, and this is true anytime that x is in between 0 and 1. This is doing exactly what a piecewise thing does. And the second part of this is dy dx. That's supposed to be a y on top. It's a pretty ugly y. Plus y is equal to 0. Now, and this differential equation is an initial value problem. This is for all x's greater than 1. We're not counting any x's less than 0. Okay? Now, our initial value here is also this initial value problem, and this is y of 0 is equal to 0. In other words, when x equals 0, y is equal to 0. Let's get that right. Yeah. Okay. Now, I just as soon do it this way. And the other thing I would just as soon do, guess what, folks? This is separation of variables. Both of these can be done by separation of variables. And I don't know why they are going to have you go through uh, the linear process here. Okay? Are you okay with just doing it by separation of variables? It's probably, yeah, it's not much easier, but it seems like it would be. So what we're going to do with the first one here is do dy dx is equal to 1 minus y. Okay? And then I'll rewrite this as dy dx, doing two things at once. I'm getting all the y's on one side over 1 minus y is equal to dx. I wrote it in differential form and moved my 1 over y under my y. Integrate both sides of that, and you get log of 1 minus y. Yes, you should say absolute value of 1 minus y. Now, I just got a message saying my internet connection is unstable. Did I break up on you there? Okay. I just got a little blurb saying my internet connection was unstable, so that's why it did that. It wasn't Zoom, it was my internet. Okay. Are, no, no, well, it could have been both. Are you, by the way, on Spectrum? Oh, I see. I wonder if it was Spectrum. Maybe the whole system had a little hiccup. I don't know. But anyway, we're back. Okay. Um, so there is the integral of the left-hand side, and the integral of the right-hand side is just x. And we can put our plus c in there if we want to. And I think here is legitimate because y equals 0 is included in this. X equals 0 is on this side. So let's put x equals 0 and see what y gets. Well, that would be the log of 1, because y is going to be 0. Log of 1 we know is 0. We'll get back to this in a minute. And that's equal to 0 plus c, so that's equal to c. So c is equal to 0. All right, so we've got that side done. Sorta, we got that side done. Here's what we have so far is log of, and I'm going to lose the absolute value bars, and here's why. Your x's are always positive, okay? And if x's are always positive, and let's just take a look at this. I'm going to leave off the absolute value bars now and see if this is okay. Minus y is equal to x, because c is equal to 0. Okay. Now, what I'm going to do is e both sides, okay? And this will be, when you e this one, I don't have enough room to write it, just going to be 1 minus y is equal to e to the x. Now, e to the x is always positive, okay? Always positive, okay? And if x is between 0 and 1, when x is equal to 0, that's 1. So y would be equal to 0, okay? And that's okay. That's where we start. That's our initial value. If x is anything, let's go all the way to the other end, equal 1, then e to the 1 is 2.7, blah, 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 blah. And 1 minus y has to be 2.7 something another. So y has to be a positive. Okay, say that again. Y has to be 1 minus e to the x. Okay, but e to the x is something less than 1 or equal to 1. Okay, and so y, I think, is perfectly fine for y to be in that range. So I think we're okay with that. So this then yields to be y is equal to, like I just said, 1 minus e to the x. That's what we get from our initial value problem of this one here. Okay. Now, the thing to note here is when x is equal to 1, which is the endpoint there, this will be a negative number, right? Y will be a negative number, and that's what made it good. I said it backwards. If y is negative here, 1 minus a minus number is always going to be a positive number. So yeah, that will be fine. But it doesn't look like that. I've done something dumb here. I can't figure out what it is yet. Okay. They have e to the minus x, and I've lost a minus sign somewhere here, and I can't tell where to find it. Did I write my problem down right? I think I did. Okay. They have c is equal to negative 1. How did they get that? It may be that my problem is my initial condition. Yes, that's my problem. No, it isn't. Okay. This should have worked, and for some reason it's not working. Of course not. Okay. You're doing the antiderivative of this thing is not that, it's minus that. Because your chain rule. Okay, the chain rule. Okay. So that's the left-hand side is that. So what we're going to do is then have, so then when you plug this in, when so that would then make this be a minus here. Let's see, when y is equal to 0, x is equal to 0. Okay. So what we'll do at this stage, I think I'm okay here, is we'll multiply both sides of the equation by, let's see, yeah, by minus 1, and this becomes the log of 1 minus y is equal to negative x multiplying both sides. Yeah, that's supposed to be an x. And my eraser is still not working. Okay, let's see. That's not working either. Okay, nothing's working. This is an x, negative x. Okay, sorry about that. I can't get my eraser to work. So then you e both sides of this, and you get 1 minus y is equal to e to the minus x. So you get y is equal to 1 minus e to the minus x. Yeah, that was it. I forgot my chain rule there. So yeah, that works out. Okay. The antiderivative of this would be log of 1 plus 1 minus y times a minus 1, because you have the chain rule in there. Sorry about that. I forgot that one. Okay. Say again? Yes. What's the question? Okay. Uh, if I see your steps, if I see where you're doing, and you made just a dumb mistake like that, of course you're going to get partial credit. Uh, it's not an all or nothing. My older brother was saying the answer is really important, because I said I give partial credit. We were just talking about things in general. And so, no, yeah, but you just don't need to make the same mistakes I do. Okay, no, I'm just kidding. Yeah, you, and that happens, but you're going to get um, partial credit if I can see your work. So please show me your work. And there would be a perfect example of that. But I just knew it wasn't coming out right because it wasn't making sense. Okay. But this is making a little more sense here. Okay, that's the left-hand side. Now the point here, what I was trying to make is when x is equal to the other end of this, 1, then this would be y is equal to 1 minus e to the minus 1. Okay, well, that's going to be a special number, so when we'll get to that in a minute, but when x is equal to 1, y is equal to 1 minus e to the minus 1. That's going to be our initial condition for this one. It's not really initial, it's when x equal 1, but it's this end, because this thing's got to match this one. It's a piecewise defined function, but they can't be, the solution can't be a discontinuity. Okay, so let's do the same thing here, but let's do it correctly on this one. This will just be dy dx. Separation of variables works here. Is equal to minus y. So now that gives us dy over y is equal to a minus x. Okay, integrate both sides. That gives you a log y. This time we can say that is equal to minus x squared over 2, right? Integrate both sides. Oh, I left off my d. Wait. What was I doing? This is a, where did I get a minus? This is a dx. Goodness gracious. It's a minus dx. Okay. Minus dx. So this, when you integrate, gives you minus x. I was jumping ahead and already doing the integration in my head. Okay, log y is equal to this, and we'll put a plus c here again. Okay. Let's do, we're okay. So let's e this side, and that gives you y is equal to e to the minus x plus c. Now that's a little awkward. Now this is not the same c as the c before. I should probably give it something else, but this is a different problem. So understand that's a different c. This time, here's the, you might say, initial condition. When x is equal to 1, y has to be equal to 1 minus e to the minus 1. So this will be, I can't hear you. That's log y. Yeah. Okay. All right. It's not really a number, it's an expression. It's the integral of dy over y. That's log y. Integral of dx is, and that's a minus dx, is minus x plus c. Okay, and then we e'd both sides to get this to be y. Now, we're going to plug this value in when x equal 1. So this is going to be a 1 minus e to the minus 1 is equal to e to the minus 1 when x is equal to 1 plus c. Whoops. Yuck, I can't change it. It's not going to change. This plus should be up here with this. Plus 1. No, plus c. Is a c there. Okay. Now, I regret how I did this now. This is not there, so just ignore that. Okay. What we're going to do is solve for c, and here's how we're going to say this. This is the same as e to the minus 1 times e to the c. Do you see? When you have one base raised to a sum or a difference of exponents, is the product of the base of those exponents. So this is your new constant, okay, which we can call anything you want to. So we have 1 minus e to the minus 1, that's your y value when x equal 1, is equal to, let's call that c. We won't be this as c anyway. C e to the minus 1. Okay. Now, we need to solve for c. We're going to divide both sides by e to the minus 1. Okay. So here these go out. Of course, these will go out too. And you wind up with c, this new c, this is a different c. C is equal to, and e, 1 over e to the minus 1 is just e, okay? So c is equal to e minus 1. That's not to the minus 1, it's minus 1, okay? So our solution for this side is this. Y is equal to e to the minus x. Boy, the pen is just going anywhere it wants to. E to the minus x. Now this is the new c here. So this is the coefficient of that. I shouldn't have written it that way. Let me do away with that. Y is equal to e to the minus 1. That's our C. E to the minus x. Now, there are other ways you can write that. Here is one of them. Y is equal to let's add those two exponents together because you've got the same base, different exponents, and you have e to the minus 1 minus x, I think is a legitimate answer. Let's see what they give. They had it the way I did the first time, this one right up here. They didn't change it. So here is their solution for that one. Now you see what we did here. I used separation of variables both times. If I hadn't made a stupid mistake here, that would have been helpful. But you get a solution here for using this initial condition here because this applies to this side only. That's where x is equal to 0. Okay? So you apply that here and you get your y value at any value for x. Okay? You do the same thing here and you wind up with something that looked like this. However, your initial condition here would be when x equal 1, it has to be match what this is. And that's where all these other things came in. That's where the 1 minus e minus 1 came in as your coefficient here. So maybe we'll see if the book's rendition makes it any clearer. I know mine's all over literally all over the board here. Okay. Now, they did it by linear technique, which not sure why, but they came up with this. Okay. Here was our initial condition, and they said that's equivalent to this. Well, what they did the p of x is equal to 1, integral of p of x dx is equal to x, raise that to the e, and that's your e to the x. So that's what they did. They multiplied this by both sides. E to the x was the integrating factor. Now they skipped a bunch of steps to do it. It made it look like that was simpler and easier, but it really took just about as much writing. And integrating the last equation, this one, that would be e to the x times y is equal to e to the x, okay, plus c, okay, or c1 they call it. Now their c1, the way they wrote it here, because they have a plus c here, then the next step they do that they skipped is divide everything by e to the x. That's why I say their rendition to me is not much clearer because they skip so many steps. And when you divide this by e to the x, you get 1. And divide the c1, which they called it, by e to the x, you get c1 e to the minus x. And then they applied the initial condition to that. And they got their c1 is equal to negative 1, which then gave, and they don't even write that down. So it should be y is equal to 1 minus e to the minus x. That's what we got. They didn't write, oh, there it is. I'm sorry, there it is. Y is equal to 1 minus e to the minus 1, minus x, okay? And that's good from 0 to 1. Now for x greater than 1, this is the thing, and they skip every step possible here and say y is equal to c2 e to the minus x, okay, without any explanation of how they got it. Is true, I'm sure, but what I was saying as a new initial condition basically was saying appealing to the definition of continuity. You want this answer to be continuous to x equal 1, so we put x equal 1 in here, and y equal 1 minus e to the minus 1 here, and that gave us a way to calculate C2, which came out to be exactly what we got. So, in the first part is 1 minus e to the minus x. That's what we got. In the second part, remember, I gave you a different rendition of it, but I said they went back to this one. E minus 1 is your coefficient, e to the minus x there. And it starts here, goes up to there, and then is an exponential decay here. That's what this is showing. This one here is showing the exponential increase here, because as x gets larger, this term gets smaller, and you're approaching 1. You don't ever get there because you reach there first, and then you go down from here. And that's your transient term down here. Now, what they should have done, I think, no, I guess you're okay. I was going to say, I think you almost have to have an open circle here because of that. No, you're okay. So anyway, that's piecewise defined. The point is, now, they just showed you when the F, the right-hand side, was piecewise defined, and that's pretty easy. You just do two differential equations, one here and one there, because your F is either 1 between 0 and 1, 0 anywhere after. So solve this one and you get a solution there. Solve this one and you get this solution here, which with continuity, making your initial value of this one the terminal value of that one, so you have continuity there. That's what gave it to you. Now, they didn't show you what you do if your P of x was discontinuous, but you can almost imagine that as well. You just have two different integrals of P of x dx, and then you have to match things up there. So, fortunately, or hopefully, they won't give you one like that. Now, goodness, we only got 4. Yes, I see 4 minutes, yeah. Let's just talk about this error function here, okay? Because you do run into this. Are all of you engineering majors? Seems like you are, aren't you? Or any of you a math major? I can't hear, so yeah, okay, yeah, that was Corbin, yeah. Dawson, I know, is engineering. Melissa, are you? Yeah, I remember now, and I'm pretty sure Billy is engineering too. Okay, but in this, you're going to have some functions that sometimes are defined as non-elementary integrals. In other words, integrals you can't solve. And they mentioned two of these here. One of them is what they call the error function. That's this one. And the other one is the complementary error function. And if you'll notice, the error function takes you, the coefficients are the same, 2 over root pi, which is a strange number. Same on both of the cases. Your integrals look to be the same, except this one goes from 0 to x, this goes from x to infinity. Okay? Now, this integral here, the integral of from 0 to infinity of e to the minus t dt, which is basically what you get if you combine this part and that part, okay? If you were to add these two together, that gives you the 2 over root pi to be on the outside, and add those two together, you get this one. Now, that's where you get your 2 over root pi, because these, they say the known result here is that's root pi over 2, okay? They have proved in the Appendix A. So you can go back and look at that if you want to. Now, so what we know is, because that's true, and this is the inverse of that, then the sum of those two together is equal to 1. Now, where is all this heading? The probability of anything happening is 1. Anything happening, or everything's happening, is 1, okay? Because it's sure to happen, okay? Well, in other words, the probability of any event that is possible to happen, going to happen, that's got to be 1, because something's always going to happen. So what this is basically saying, these are your curves that list probabilities. Your error function, and why they call it this, there is probably a reason for that, is up to one point of x. Anything beyond that is 1 minus whatever this was, because the sum of those is 1. So, and that's what they're saying here. The error function plus the complementary error function has to equal 1. Okay? Now, they don't say where you use it or why you use it, but its importance in probability, especially statistics, of course, and applied partial differential equations. We're not going there. The error function has been extensively tabulated, and the error function of 0 is 0 because you're going from 0 to 0 there. That's going to have to be 0. And the others they say you can find there, that's all they do with it. That's all they talk about it. And that gets us to, well, no, I'm sorry. They are going to have you do a problem with it. So that's going to be next time. We'll begin next time with example 7 on page 61. And I should have stopped before I got there. So we cover all this last time. This was trying to get me to do it. No, I was too stubborn. Okay. Homework exercises. Here would be any of the odds. This is on the next page, 1 through, wow, 23. Any of the odds, 25 to 35. Any of the odds, 37 to 39. Any of these are in the back of the book. I'll put it that way. I think you can do 41. Oh, 41 is one with the P of X is piecewise defined. And then hang on, and we'll pick up with 43 after we do that, because that deals with the error function. Okay, we'll pick up the rest of those next time. All right, any questions? Last thoughts, parting shots? Okay, all right, ran over a minute, but guess what? I won't charge you any extra, so we'll go from there. We'll stop the sharing, and unless there's questions, we'll end the meeting. Take care. We'll see you on Thursday. Right? Yeah, Thursday. All right. Bye-bye.